In this lecture, I am going to review a molecular model quiz that is much like the quiz you'll see shortly in my class. So these are the things I'm asking, and these are the things I'd be asking on a test as well for different types of structures. So it's a mock quiz, and I'm just going over them. So my guess is that you have taken the worksheet that I've had posted, and you have worked through it, and you want to see how well you've done. So I'm going to walk you through it. So let's start with XEF2. Everything starts with Lewis dot diagrams. So I start with my Xe, my xenon, and I know that it is a noble gas with 8 electrons, so I put out the valence electrons. Make that 8, 4, 5, 6, 7, 8, and then I'm going to add 2 fluorines. And I put fluorine's valence electrons out. And make sure you show the lone pairs. And as weird as this sounds, we are done. We've done it. Now, this represents an expanded octet. And the reason why it's expanded is we're dealing with an element beyond row 2. Xenon, okay, you say, oh, I thought it needs to have 8. Well, it doesn't have to have 8. It has to fill all its orbitals. So let's find out how many orbitals it has, and let's show you how they're filled. So I'm going to count electrons that are in different planes. 1, 2, put the lone pairs together, that's 3, 4, 5. There are 5 pairs of electrons in different areas, or I should different dimensions, that are somehow being repelled by the VSEPR theory, VSEPR, into this shape. So the VSEPR shape, or the shape of where the electrons are, okay, is determined by really if in fact these pairs of electrons are all the same size and all the same energy, so they have to hybridize. So to figure out the hybridization, as I've just done, I figure out how many pairs of electrons I have. And of course 1, 2, 3, 4, 5 tells me that I have an S, a P, a sp3d. Now how do I get 5 out of that? Well, an S mixes with 3 P's, that's why it's sp3, and a d orbital, whatever orbital you want to draw for a d. Okay, so 1, 2, 3, 4, 5 orbitals come in, and 5 different orbitals are produced that repel themselves into this shape. So the hybridization is sp3d2. I got this all from looking at pairs of electrons. All right, now I'm going to rewrite this. You can certainly leave this as such, but I'm going to rewrite this to clean this up, to make some sense of this. Okay, certainly this is fine, but I want to make some sense of this. You don't have to rewrite it, but I'm going to. So I have xenon in the middle. I have 5 pairs of electrons that repel themselves, okay, into a trigonal bipyramidal shape. And I know in this shape the axial positions, okay, will have atoms, and the lone pairs have to be in the equator. So if I draw one coming at you here is a lone pair, another coming at you here is a lone pair, and then I've got one kind of going behind me as a lone pair. It's planar. It's hard to draw, but you've got this trigonal planar in the middle. You got this in the middle here. Any case, that is my shape. And of course, electron domain geometry is going to be linear. You should know. Oh, sorry, not linear. Okay, that would be the molecular geometry. I got ahead of myself. The electron domain geometry, where the actual electrons are, is trigonal bipyramidal. That's where the electrons are. Electrons are in this bond, they're in this bond, and 5 pairs of electrons, if they're all the same size and same energy, will repel themselves into this shape, which is the top of a 3-sided pyramid. So if I had like this top, I had one coming at you, another one coming at you, and then one into the board. Okay, if you can see that, then you would see it's a top. This is the top of a three-sided pyramid. This is the other top of a three-sided pyramid. So it's a bipyramidal. Now, the molecular geometry, just where the what? Just where the atoms are, is going to be linear. And if you remember your shapes, in the sp3d family, we have the trigonal pyramidal, what I just wrote here. If you have one lone pair, it's seesaw, or the distorted tetrahedron if you want to get crazy. Then you have two lone pairs, it's T-shaped. And of course, three lone pairs is linear. You have to get this down, but you can see how this would work. Okay? And of course, that's all the shapes in this family. It all starts by figuring out how many pairs of electrons for the central atom. And that's how you do it. Now, I did say to show your formal charges, so let's do that. Okay? Let's get rid of this. Let's go back to my Lewis dot diagram. And let's show formal charges. Let's get some stuff out of the way to make it nice and pretty and clean. Okay. So formal charges we'll do in black. So let's start with F. Fluorine has 7 valence electrons. We'll do it up here. So it starts with 7 in my structure. Remember, formal charges are just ways of bookkeeping whose electrons are where to make sure I have the best possible structure. Okay, in this structure, it's not necessary to actually have them because we're pretty confident that the fluorine will be terminal because of one unhybridized p, but for practice, we'll do it anyway. 7 valence electrons minus, okay, all the electrons that are assigned to fluorine. Well, if you look with me, all the lone pairs are assigned, and of course, half the bonding. So fluorine, okay, 7 valence electrons, and 1, 2, 3, 4, 5, 6, 7 has 7 electrons assigned to it, so the formal charge for this is 0. Formal charge is the valence electrons, all right, minus the assigned electrons. Okay? Boy, that doesn't look too good, does it? All right, so let's get rid of that. Let's go to next fluorine. Well, the next fluorine has the same deal. It has all a lone pair, half its bonding. So it'd be 7 valence minus the 7 that are used to make this work in an electron dot diagram. So it's also 0. And then xenon would be, of course, all of its lone pairs and half of the ones that are bonding. So we count for all electrons. Xenon has 8 valence, or 8 electrons, if you want to think of it that way. It's outermost, the S and the P. And of course, how many electrons are assigned to it? All the non-bonding, 1, 2, 3, 4, 5, 6, and half of the bonding, 7, 8. And you can see that everybody is 0, and that's a preferred structure. Okay, we didn't really have any other structures to write, but it shows you that this structure is the best written because low numbers or zeros are preferred. That means that the electrons that it has was used to make the structure, and that's usually the greatest possibility for a structure to have. So in any case, that's the formal charges. Proximate bond angles for this. Well, bond angles are between the atoms. So this is this is linear, so linear is always going to be 180 degrees. Okay, so 180. You wouldn't give me the bond angles for the lone pairs. The lone pairs help the shape stay the way it is in this family, but where the atoms are, we'll call that 180. Polar molecule. Well, I should have put an arrow to show polarity if this was a polar molecule. Now, one way to do that is to show dipole moments. So the partial negative sign would be for the fluorine because it's more electronegative than the xenon. The partial positive side of the bonds are here. And as I've told you before, positives go toward the negatives. So you're going to have 2 dipole moments. These 2 arrows are vectors. They have direction and they have quantity. And the size of the arrow is basically based on the difference in the electronegativity. Well, because this is both an F to Xe bond, they're both the same, the size would be the same. Therefore, both of these arrows would cancel, and there's no overall dipole moment. There's polar bonds between the F and the Z, but the molecule is nonpolar because the dipole or flow of charge, okay, cancels. or we say the molecule is symmetrical. It's all the same thing. So this is a nonpolar molecule. Having fun yet? Okay, maybe not. Sigma bonds. Sigma bonds are direct overlap. Well, any one bond. Okay, so a one bonded bond or singular bond has to be a sigma bond. Okay, now how do I know? It has to be a direct overlap. The first bond has to be a direct overlap. The second and third are the pi bonds, and when we draw that one on the below, you'll see that. So number of sigma bonds. We're going to have 2 sigma bonds. And the reason why there's 2 sigma bonds because we have 2 single bonds. Okay. Moving forward. Pi bonds are 0 pi bonds because we don't have a double or a triple. Resonance, no. No need for resonance here. There's no double bond somewhere else in the molecule to make this work. Okay. And last question. Extra credit. Okay, draw the orbital diagram. So let's try to draw this, and this might help you see what's going on. So we have a hybridization at sp3d, so we have 5 orbitals, so I can draw that. So I'm going to draw 5 orbitals. Here's 1. Here's 2. These are not p's, these are sp3ds. Then we're going to have that trigonal planar in the middle. So we'll have 1 coming out here, 1 coming out here, and 1 coming to the back. All right. So the blue is equal to sp3d orbitals. Okay. No unhybridized p's because all the p's have been used. Let's put the valence electrons out. Okay. Let's do. It has 1, 2, and 3, 4, 5, 6, 7, 8. Who do we appreciate? Nobody. Got it. Now, let's do red is equal to unhybridized p's. Well, because F is bonding terminally, okay, it's bonding at the end, so this is an unhybridized p. Okay, for lack of planning, there's 1 p, there's another p, and there is the third. We have the circle, and we're going to put some valence electrons, make them black. It has 7, 1. Here's 2 in the S, 3, 4, 5, 6, 7, 8. Can't put this here because there's 2. There's the first bond. There's the first sigma bond right there. And we're going to do that again down here, although I didn't give myself enough space. So we'll just kind of overlap more. Here comes 1p. Here comes another p orbital. And here comes the 1. That's a pz. And then we have our s. Let's put in the valence electrons. I'll make them blue to make them see. So here's 1, 2 in the s, 3, 4, 5, 6, 7, 8. Who do you appreciate? Nobody. Okay. So there it is in all its glory. And that would give you extra credit. Extra credit for me. Amazing in my own area. All right. So that's halfway done. So that's the first half of the quiz. Second half. Here we go. SO3 -2. That -2 is screaming to me add 2 electrons. So trial and error. S. And I put 3 O's. I put out electrons. I have 1, 2, 3, 4, 5, 6. That's the sulfurs. And then I have 1, 2, 3, 4, 5, 6. The oxygens. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then I have 2 more. We'll make them, I don't know, make them white. Yeah, that'll make sense. Let's make them orange. Okay, so I got SO3 -2. I added 2 electrons, and let's see what we have here. Okay, now I don't know if this is correct. I'm just throwing electrons out. Now, by just looking at sharing, this oxygen has some problems. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I cannot have 10 electrons for an oxygen. I can have 10 for the central atom because sulfur is in row 3. It's not bound by the octet rule, but oxygen must have 8. So I cannot put this pair with an oxygen for a double bond. So this pair is going to have to go by itself on the sulfur and not bonded to an oxygen. If I try to take these, if I try to put this pair here and move this somewhere else, you have the same problem. This pair cannot go with an oxygen. We cannot double bond an oxygen with its 6 because it'll have 10. So we're forced to put this pair somewhere else. All right, so let's take away some of this stuff. Let's go backwards a little bit, maybe, and take these away. And oops, there's a dot there I'm missing. 6 valence electron. First missing July. We're missing stuff. Hold on, let me rewrite it. So we've got oxygen with 6 valence, and we're going to put this pair we said was let's say orange over here. Okay. Now, by looking at some things, this oxygen is sharing 8, this oxygen is sharing 8, and this oxygen is sharing 8. And I have a lone pair. Now, I'm going to clean this up a little bit because I see that this lone pair is going to change something. Because if I count things, let's go with yellow for a second. If I look here, this is 1 pair, 2 pair, 3 pair, 4 pair. I have 4 pairs of electrons surrounding this central atom. So I want to draw that more indicative of the structure. So I'm going to rewrite this, okay, like this. So I have a sulfur, and I have a lone pair. That's what this came from. Then I have the rest of my valence electrons, which are 6. Remember, we added 2 from the environment. Then the oxygen brings 6. And I have 3 of them. And there I go. And I may say, well, let's see what it works. Oxygen shares 8, this has 8, and sulfur has 8. You may say, well, this is a good structure. All right. Now, what if I was to make a double bond? I know that oxygen loves a double bond. Heck, who doesn't? So if I put this double bond here, why can't I do that? Why can't I do that? Because sulfur, this guy now has 8. Sulfur has, what, 10, but I know it can. So how do I know that I can put a double bond there or not? Well, my friends in chemistry, the answer is formal charges. Let's see if this is the correct structure. So let's do some formal charges. So this oxygen, it has all of its lone pairs, half its bonding, and we get 1, 2, 3, 4, 5, 6, 7. So 6 minus 7 is the assigned. This is a -1. This oxygen has the same scenario. 7 assigned electrons, that's all of its lone pairs, half its bonding, and we take its valence, which is 6, minus its 7, we get the -1 also. And as you guessed, this oxygen has the same scenario, single bond, so we should get the same scenario, -1. And then sulfur has all of its lone pairs, plus these guys right here. It's 1, 2, 3, 4, 5. 5. Well, it has 6 valence minus 5 is +1. All right, so we got +1 and we have -3. Notice the whole thing equals -2, so that's a good thing. But, party people, can we improve on this? -1 and +1 means that there was a transfer of electrons. Can I give myself some zeros? All right, I want to have some zeros. So my best bet is make a double bond. So what I'm going to do here, take this away. Okay, take this away. And what I'm going to do is make a double bond. So I take these 2 bonds, and now I'm going to put them right here. I just move them around. Now let's do this again. Oxygen, all of its lone pairs, plus half its bonding. And you see it's 6 valence minus the 6 assigned now by adding a double bond. Okay, I've lowered this sign number because it's sharing that now. So now this is 0. That's a better structure. Let's redo sulfur, okay, because we kind of messed around a little bit. So let's redo the sulfur. All of its lone pairs, half its bonding. We get 1, 2, 3, 4, 5, 6. Hey, 6 minus 6, 6 valence minus 6 assigned gives me 0. So by putting a double bond here, I have created a better structure by having 2 atoms with 0. So the best structure, party people, and let me just redraw this. Again, this should be done in pencil. Okay, it's a lot of trial and error to figure things out. So the best structure is sulfur with a lone pair, double bonded to an O, single bonded to an O. Make sure you put the lone pairs out. Single bonded to an O. Whole thing is -2. So I got my brackets to be polite. All right, I should have them here too. That's the best structure. Now, anyone think of 2 other structures I can draw? Yeah, this has resonance, doesn't it? Couldn't I put the double bond here or here? Yes, I could. So I would need to have, if I was to do this correctly, 2 other structures. Okay, so let's get rid of all my other work below. So I would need 2 other structures. So let's do it. Double arrow to show that it kind of blends together. Sulfur, single bonded to an O. Don't forget the lone pairs. Single bonds will have 6 lone pairs. Double bond over here, 2 lone pairs. Single bond here. It's -2. And I need one more. Sulfur double bonded here. It's what? Double bonded to the O in the bottom. Single bonded to the O here. Single bonded to the O here. And this, of course, whole thing is -2. If I could write smaller, that'd be cool. The formal charges, of course, just on one, and we showed that already, but I'll just put out here just in case you want to see it again, is, of course, 0 for the double bond, -1 for the single bonded, and 0 for the sulfur. Total charge of -2. Okay, so let's answer some questions here. Resonance, yes. And I knew it needed resonance because I had a single bond that could be in other parts of the structure. Now this should bother somebody. I'm probably saying, hey, I got a question. Okay, and we'll see if you are on with those people that are bothered right now. What's the hybridization? Okay, how do I figure that out? Find pairs of sigma bonds, or pairs of electrons in different areas. 1, 2, 3, 4. My friends in chemistry, or my enemies if you hate this. Hybridization has 4. So I need an S, 3 P's, and of course a D. Christmas in July, no D. Just sp3. What am I thinking? sp3. All right, how do I know? Just 4 pairs of electrons. So an S and 3 P's come together to make 4 equal sized energy orbitals that repel themselves by the VSEPR theory because of repulsive force electrons into a certain shape. Now the shape of the electrons, if it's sp3, okay, is of course a tetrahedral. The geometry of where the atoms are. Well, we have only 3 positions here. So in a tetrahedral family with 1 lone pair, you should have the top of a 3-sided pyramid. So this is trigonal, pyramidal, or a triangle pyramid. The bond angles, well, it's a tetrahedral, so that drives it to be 109.5. Now, because of the lone pair, it's going to be a little less than that. That little lone pair is going to bend it more. Polar molecule. Well, does this have polar bonds? Yes. Is it asymmetrical? Yes. So this would be a polar molecule if it didn't have a charge. But because it's ionic, it's not applicable. Ionics are never polar or considered nonpolar. Okay, they are just ions. The whole thing is -2. If that wasn't charged, you're right, that'd be asymmetrical and you'd have a negative and a positive side. But because it's charged, it's an ion. Ions bond ionically and they don't have a positive or negative side. The whole thing is -2. Okay? Number of sigma bonds. Well, we'll do one of these structures. I know they're blending all three, but we'll count 1, 2, 3, and then 1 pi bond. Even though that pi bond is being stretched over the 3 atoms, we'll just count one structure. I understand where you're going with that. So we have 3 sigma, 1 pi. Hey, Mr. Zagrodsky, please draw that for me. Whoa. And my answer is, I can't. It's not that I don't want to. We have reached the end of our theory here because, as some people are probably saying to themselves, how in the world can there be resonance? I learned today that to have a double bond, I need a pi electron. Well, if this is sp3 hybridized, there's no p's left. So how can I have a pi bond here, here, and here in 3 directions if it's sp3? And you know what? We're all perplexed about that. What we're saying is we've gotten to the point where we've used these dots to tell us so much information, we have to rely on experimental evidence to see if in fact the structure is what we get from formal charges. So we do know that experimentally, and this is not something you'd have to know, I've told you before, pi bonds occur from unhybridized p's. Okay, I've taught you that. This doesn't have an unhybridized p. So how does it do that? We don't know. Okay, so we're at the end of our valence bond theory. So the only thing you can do is just follow the formal charge rules to find the best structure. Does that always work? And is it always parallel experimental evidence? No, it does not, and I'll speak more about this. But in terms of what I want you to do, and any professor in college, make the best structure based on formal charges. And we'll talk more about how there are some problems with this theory. Okay, so I hope that helped. And that's how you go about doing this. All right, good luck tomorrow.